Finally, to get our best estimates, we have to minimize the loss. Let's roll up our sleeves and do this thing. Here's the function that we have to minimize. Before we get to taking derivatives, it is a good idea to look at sizes and shapes. Theta is your vector of parameters, and I imagine it as one column, and n is the number of individuals you have in your sample, so you're adding over all of them. For each individual, you have a contribution here to your loss. For each individual, this yi is either a 1 or a 0. So this is a very simple thing. Here you have the vector of features and the vector of parameters, and the dot product between the two of them is a number. And then you take log of sigma, remember, creates a probability of your the predicted probability for the response of this particular individual. So we have to take derivatives. And we have to take a derivative with respect to this vector theta. So here, everything that does not involve theta is a constant as far as our differentiation is concerned. Now, we are going to take the derivative, and we have taken the derivative inside the sum. I should point out that just to avoid writing too many parentheses, we don't have a parenthesis here and at the end, but it's assumed that this entire thing to the right of the sum is the contribution from record I. And so this whole thing is being summed, I equals 1 to n. Right, so we have to differentiate. So here is the derivative of this function with respect to theta. Now, what kind of function of theta is it? yi is a 1 or a 0. And this is a linear transformation. So when you have the derivative of a linear combination, all you get are the coefficients. And that is what has happened here. On this side, we've just left the term as is. We have to differentiate log of the logistic function of this linear transformation. And clearly, there's going to be some chain rule involved. Now, if we carry the terms down, we carry this one down as is, and now we have to differentiate log of the logistic function of a linear transformation. The derivative of the log is 1 over the argument of the log, so that's what we have here. And now, chain rule, we have to take the derivative of the argument to the log. So that's why you have the derivative of sigma of this linear transformation. And that is why we had examined the derivative of the logistic function, which happens to be rather nice. The derivative of the logistic function at any point t is the function at t, the original function at t, times the function at minus t. So plug in chug. Our derivative is the minus 1 over n is being carried down, the sum is being carried down, the first term is being carried down, this denominator has been carried down here, and now at the top we have the derivative of sigma at this point, which is sigma at this point, right there, times sigma at minus of this point, which is right here. And we're not done, because we now have to differentiate this, the argument of sigma, with respect to sigma. But the good news is that here is a linear transformation. It's a linear combination of the sigmas, a linear combination of the thetas. And so in the end, we are just going to get the coefficients. And in that one term, we have collected a few terms. So we have yi times phi of xi, yi times phi of xi. and then minus y minus because of the minus sign here. When you differentiate this linear transformation with respect to theta, you will get minus phi of xi. So this is a cancellation, and you are left with just sigma of the linear transformation, which has come down here, and times, of course, the phi. This is a much friendlier looking function than some earlier forms of the derivatives that we had. And our job now is to set this equal to 0 and solve for theta hat, which has no analytic solution. And so we need numeric methods, and you know exactly what those numeric methods are. They are gradient descent and stochastic gradient descent. So gradient descent for logistic regression, this is the ordinary gradient descent algorithm that you carry out. This is just the function that we are entering into the algorithm. This is the derivative that we found. We've just flipped a sign. There was a minus out here, which has been taken inside. You can also do this by stochastic gradient descent. You just take exactly the same function, but take a random subset of indices in some set B, any number of random indices, could just be 1. And you know that these two algorithms are very similar, and you know now that this random sample average in the stochastic gradient descent algorithm is an unbiased estimator of the overall average over all records. Scikit-learn will do all this for you. So again, from sklearn linear model, you import not linear regression, but logistic regression. And then you do exactly the same thing that you did for linear regression. So you can define your model to be now logistic regression. There is the regularization parameter, which is included by default. It's a small number. What you have to specify is 1 over that. So it's typically a big number that you are specifying. And then you fit your model, you have your features and label. You can make predictions of the ones and zeros, and you can make predictions of the probabilities. And all this is much better understood in a notebook.